Our speaker today, Dr. Andrew Hamilton, who currently is the Engineering Division Chair at the Monterey Bay Aquarium Robotics Institute. And I've been very excited to visit their facilities a few months ago and find out that they have a lot of very exciting projects and maybe also opportunity for collaboration. So I thought I would invite him and give a talk here for everybody to get familiarized. I want to make sure we are broadcasting. Okay, perfect. So we have some people in the Zoom room. So, by the way, Andy received his BS from University of Colorado and then PhD at University of California, Berkeley. And he's very interested in energy harvesting, deep sea navigation and mooring. And I would imagine that involves also control aspects and motion planning and architecture, manipulation, all sorts of very interesting problems. And his institute is no more than 30 minutes away from here in Moss Landing. So welcome.
Wonderful. Thank you, Ricardo. Really appreciate the invite to come here. One of the reasons I came and we wanted to do this is exactly that. You know, I've been down there at MBARI for many, many years, and this place is here, and we haven't done a ton of collaboration over the years. So I think there's definitely room for some of that. We have some formalized programs to do that sort of thing, as postdoc, internship type stuff, and then also other possibilities that could be explored on a case-by-case basis. So I think for everyone here and online, you keep that in mind as we talk about these things. I think it would be a neat way to kind of expand everybody's reach a little bit. So, but what I'm going to talk about today is a little bit, I'm going to touch on the origins of our institute and what we're doing at MBARI. And then I'm going to talk about some of my projects, which are really about energy harvesting, for the purposes of repowering autonomous underwater vehicles, for the purposes of oceanographic work. So, Monterey Bay, yeah, we got, we're not advancing. It's not what we tested this. All right. I could do the whole talk just from this slide. Won't be as good. We really did test it. I showed it. Oh, screen sharing. Yeah.
I'll restart that.
Okay. Right. Great. So slight delay, but that's okay. So the Monterey Bay Aquarium Research Institute is located in Moss Landing. So of course we're here in Santa Cruz. Monterey is down here at the bottom, and Moss Landing is right in the middle of the bay here. And you can see that the submarine canyon comes right up to our door. And because of that, we have access to deep water a lot closer than most oceanographic institutes in the country. Woods Hole Oceanographic Institution, which is a big one on the East Coast, of course, you have to steam in your ship for a day or a day and a half to get to water over a couple thousand meters deep, where it's quite close here in Monterey Bay. So for that reason, a lot of the work we do on the engineering and science side is deep sea stuff. So benthic ecology, deep sea animals and fishes and seafloor mapping and that sort of thing in the deep sea. And then that drives a lot of our engineering in the direction of deep sea work. So we're very familiar with putting things at deep depths and protecting them with pressure housings and that sort of thing. This is
So how deep is the deep sea?
How deep is the deep sea? So the deepest part of the ocean is about 11,000 meters deep, which is ridiculously deep. About 90% of the ocean is shallower than 4,000 meters. So most of our equipment, we will typically design to be to 4,000 meters, which is deep, 6,000 pounds per square inch at 4,000 meters. So pressure vessels are significant. We do some work down to 6,000 meters, but typically not. But below that, you start to get into a difficult balance of structure versus equipment. And it gets very different, becoming very specialized vehicle to go below 6,000 meters. It's a good question. Sorry. This is, well, we could talk about that, but
Like how deep can you get right there in the bay?
4,000, within a day's steam, it's 4,000 meters. Yeah. Yeah. About 100 miles out is 3,000 meters or so. That in the canyon also. Yes. We do a lot of deep work. A lot of what we do, as I said earlier, before we really started, MBARI is organized with a science division, an engineering division, and an operations group. And each of those groups are about equal size. So I'm going to talk, I'm the head of the engineering department, so naturally I'm going to talk about that. But I think a lot of what the engineering division does in our development work is enabling autonomous exploration in the ocean, deep sea exploration using ships and remotely operated vehicles with tethers that come up to the ship and are teleoperated by people on the boat are very powerful tools, relatively routine. You can buy that equipment from companies that service the oil industry. So a lot of the vehicles like this one, this is on the back of our ship. This is a remotely operated vehicle, which has a cable that goes to the ship and operates that way all the time. We don't do a ton of engineering development around that anymore. Sometimes we'll get involved in some structural things or something, but there's a whole lot going on there. A lot of the more interesting, from our point of view, development is around autonomous vehicles like this vehicle here or this vehicle here, which do not have a tether to the ship or battery operated, and you push them over the side and you hope they go down and do their mission autonomously, and you hope they come back. Usually they do. So I'd say the last 20 years, we've really worked pretty hard on advancing that field. I'll talk a little bit more about that. One of the big autonomous underwater vehicle development projects is what we call the LRAV, the Long Range Autonomous Underwater Vehicle. Maybe not the most creative name, but we at this point have 13 of these things, which are a 12-inch diameter vehicle, and battery section and computers, propulsion in the back. And then each of these different nose sections typically houses a different science instrument for different purposes. So I'm going to talk a little bit more in detail about that vehicle and how we're using them as we go through here. But the point here is that, a lot of the work we do is around autonomous drones flying in the ocean by themselves. When I started there in 2002, an AUV was something we put in the water for an afternoon or maybe 24 hours overnight. And we keep the ship on site with the sonar pinging on it. They're like finger hovering over the abort button. And if anything went wrong, we'd hit the button, it would drop a weight and we'd come back up. Now these vehicles are operating pretty much all the time in Monterey Bay. They have about a 2-week endurance. This fleet of vehicle has about 30,000 hours of use over the last 6 or 8 or 10 years. And we're pushing that beyond. So sweet. A lot of what we do, with this vehicle is really trying to enable the idea of a persistent presence, getting away from needing the ship there. We're down to vehicles that'll be there for a week or two. Now we'd like to push that out to vehicles that are more or less resident in the environment and able to stay there for a long time. And to do that, you need a number of pieces of technology. One is the vehicles with the capability to do what you want to do and reliability to sort of not just fail all the time. Anybody that works with robotics knows that they just kind of fail sometimes. Certain amount of autonomy. There's very much communications underwater. There's no radio waves underwater that go very far, so very limited in communication. Of course, you need instrumentation on those vehicles to do the work you want to do. And the area I'm interested in is energy on these vehicles and repowering them, because you're limited really to what you can bring along in batteries in many ways. That's the energy options here in the lower left. You can bring the energy along in batteries, or you can collect the energy from the environment once you're there. There aren't really a whole lot of other choices. The graph on the right here is sort of a little fanciful, but shows the theme of batteries, depending, no matter how much money you spend, batteries, as the deployment duration goes out beyond a month or two, the amount of energy or power available at any given moment, and I've normalized it here per like kilogram in a housing or something. We could argue about the normalization there, but what is true is you have this sort of terrible 1 over time decay of the amount of power available depending on the length of the duration. So the duration of the deployment. So this is a fundamental limitation that keeps us from having our vehicles out there for 6 months. If you want the battery this big, 6 months, you can only draw a few hundred milliwatts or something at a time, which isn't enough to drive the propulsor and the sensors and all of this. The alternative is to collect energy from the environment, either from solar, when there's not a whole lot of options. One is solar and wind system, or as I'm going to talk about, wave energy system. And then these are much more complicated systems than a battery. There's a lot of moving parts. There's a lot that can go wrong, but you don't have this decay in time. They're out there all the time. As long as the vehicle can transfer energy from those systems to your instrumentation, you have a more constant source of energy. So that's sort of the motivation for why we're doing some of these things. To that end, a project I've been running for the last while now, 10 years or so, is wave energy extraction. And we've developed this device, that's a photograph of it there on the dock before deployment. But this is a point absorber wave energy converter that has a surface expression, a buoy that floats on the top of the water, and sort of down about 100 feet down, 30 meters down, there's like a big upside down umbrella that doesn't want to move through the water very much. So there's a differential motion, as you can see in this cartoon, between those two, and that represents energy. Force times distance is work. So we've developed this power takeoff device, which is a hydraulic piston, which as this motion occurs, strokes a piston in and out of a hydraulic piston, in and out of a bore, pumps oil through a hydraulic motor, which spins an electric shaft, which is coupled to an electric motor, which puts out three phases of electric energy at different voltages. And then that needs to get converted to a battery bus voltage that can charge a battery, store it on the vehicle, and use for subsequent use. So I'm going to talk a little bit about some of the details of that technology and what we've developed there as we go along here.
Just out of sheer curiosity, what is the efficiency of that whole process from energy I'm extracting to eventually in the battery that I can get?
Yeah, well, you're asking an excellent question. The efficiency, it's a death by 1,000 cuts.
Yeah.
Every step along the way is 95% efficient, and you have 8 of those, and you get 0.95 to the power of 8, and you end up with a distressingly low number.
Yes.
In this case, the mechanical power, if I hook up a hydraulic ram to the end of the piston and put power in that way, force times speed, to electrical power that's being delivered to the battery at the battery bus voltage, is about 65 to 75%.
That's not bad.
So we're pretty happy with that. But that's taken a lot of reducing each of those cuts to more like scratches. So yeah, it's a good question. And a big change. That is a problem with and then reliability. This system is deployed for like nearly a year at a time. So you're talking several million strokes of that piston, which is a wear problem. For a long time at MRA, this is a solar and wind type style buoy that is very common in oceanography. And this is one we had developed many years ago that has solar panels on it and a wind turbine at the top. It's like about as much solar panels you could put on that size buoy. And that was about a 50-watt system, weighed about 5,000 pounds, anchored to the seafloor. It was about a 50-watt system. The wave energy system I just showed you is a similar size buoy, more complicated, but is more like a 200 to 300 watt system on average. So through the sea, some days real windy, like this afternoon is probably only making 75 watts or something, but on a stormy day, it'll be making 1,100 watts on an hourly basis. So I'll talk a little more about the power capture there, but that's a little bit of the motivation for kind of going through the trouble of wave energy. It's like, that's the only way to get these higher power numbers. This is some details. It's about a 10-foot diameter buoy, 200 watt average, I said, and we do regular deployments. This system is out in Monterey Bay most of each year. It's ashore at the moment, actually, but most of each year it's deployed in Monterey Bay. And this is, it's a little seasick at the beginning, but I do like to show this video to sort of show the nature of the hardware. This was a dive inspection where our group went out and swam down and took a look. This is the buoy, and this is the power takeoff device that they're swimming down and making an inspection of. And it's a piston inside that steel pipe. And then they get down to the bottom. We don't have to watch the whole thing, but they have a fun day. I don't know if there's any jellyfish in this picture or not. Anyway, that's the hydraulic system here with some of the power converter and motor takeoff. I'm going to talk more detail about that here in a minute. Yeah, so last year, 2023, we were out for 232 days. We just recovered it in 2024. I have an updated slide, and it was a similar 230-day deployment or so. The hourly mean power is, like I said, averaging 200 watts or so. That comes in hourly, and the max power is like 6,000 watts. So every wave comes and delivers 6,000 watts. You get an average of 200 watts over your hour, but it's in these kind of hard to deal with 6,000 watt gulps. So this is a very difficult part of wave energy conversion, is this very high dynamic range of energies. And I'm going to talk more about that. There's a whole lot of telemetry coming off the buoy in real time. That's sort of plotted on our website. You can look on these graphs, or I can give you the link. This is a public sort of website. Some design features of this system are an electrohydraulic power takeoff and pneumatic spring. I think I described that section a little bit. It has a hydraulic system to provide a damping force relative to the speed at which the piston is moving. But of course, you need a spring, like it's engineering. There's a spring mass damper system every time, right? So you need a spring in this system, and it's a pretty strong spring. It's about 2,500 pounds per meter of extension. Sorry to mix the units, but and that's done with the pneumatic spring. So there's another set of pistons and seals here with a gas on one side, so it's compressing a gas, which isn't perfectly efficient, another efficiency loss, but effective. So
efficiency loss, heating the gas that then gets cooled through.
Yeah, that's the loss. Yeah.
Yeah.
The heave cone down 100 feet down has these electric doors that can open and close. So one thing you learn in this business is if you want to make more power, the way to do it is to make this thing down below bigger, because the added mass of this system, the amount of water that it has to accelerate when it accelerates, is proportional to like the diameter cube. So you make it a little bigger, and that added mass gets bigger and bigger. The natural frequency of this system is like too short already. So as you make that mass bigger, natural frequency is square root of spring constant divided by mass. So as you make that mass bigger, the natural frequency drops towards the excitation frequency of the waves, and everything gets better. The problem is, so in calm weather, you want a really big plate down here, and then the storms come and everything breaks. So the solution here, and I think really every wave energy converter kind of needs this adaptability to conditions. This is sort of a result of our experience. These doors, these green doors, open. So in wavier conditions, it closed and it looks like this. And then or in calmer conditions, and as it gets wavier, that opens up and vents a bunch of fluid down here through the center. And the added mass and the drag of the device drops dramatically, and the loads drop dramatically as well. So we're adjusting that depending on the conditions. So that's a key feature of the system, which is actually pretty simple. But before we had that, we broke a lot of stuff because as soon as the big waves came, it would just, the loads were too high. Yeah.
So does it jam with, it looks like you're rotating it? So
Yeah.
A shutter?
Yep, it rotates, that's right. So it doesn't have to fight the
Do
floor.
you ever have problems where you're trying to rotate it and then the motion of the water jams?
So, I mean, it's the way this works is, this is a torque motor. So it's configured in a torque mode with a big gearbox. It's like 1,000 to 1 gearbox or something. There's a little motor in there.
Yeah.
So the command to open or close the doors is a torque command for like a period of time, 2 minutes.
And so in the middle, it moves.
Yeah. So when it's falling, these doors, you see these stiffeners don't go all the way out. So these doors flex up a little bit and all the friction goes away around the edge. And then when it's getting pulled up by the
They
waves,
slam shut, yeah.
oh man, they're pinned down. That thing's not moving. So it just waits.
Okay.
Yeah. So a little mechanical design detail there.
I have a question.
Yeah.
Why is the importance of having such a long shaft between the buoy and the keep cone? Is it just because there's a big differential in how the?
Yeah. So this has about a 2 meter stroke, the piston.
Okay.
And we'd like to have the waves can be as high as, our environment, 8 meters. So we'd like to have more, but at every, 2 meters here, 2 meters here, and 2 meters here, it just practically becomes as short as we can make it. That's as short as we can make it. If it was, we'd love to have another meter of stroke, but it would add 3 meters to the total length. So yeah, there's a lot of design details in there. But for this group, I think an interesting part is the power electronics that load the rotator motor. This, as I said, is a hydraulic motor coupled to an electric motor. And I'm going to speak a little bit more detail about the power electronics, but that's a very specialized item because of the efficiency needs. There's some very strict requirements on those power electronics to make it work correctly. So we ended up having to kind of do some development around that ourselves. And I'll talk about that a little bit more. At the moment, we have a 6 kilowatt hour battery on the buoy. We're going to upsize that a little bit. I just got back from Detroit at the nation's largest battery show, where I went to a big lithium battery trade show where we thought everything to do with batteries, from mines to battery management systems to cells to paint, everything. So then on the buoy itself, we have 24-volt network and an Ethernet network and a bunch of instrumentation up there, and computers and telemetry computers and control that had a Linux control computer on the buoy, like a Raspberry Pi level computer that has a cell phone connection back to shore. So we can communicate with this system all the time. The power electronics, as I promised, I wanted to talk a little bit about. As I said, the power takeoff, this is now turned horizontally to fit the slide, but there's 2 oil chambers, and as the rod strokes back and forth, it pumps oil through this hydraulic motor and converts, so that's shaft power connected to an electric motor with an encoder, and then there's a 6 transistor drive and a controller for that, and a battery and a load dump. So one important thing in wave energy is you need to load the system all the time. So if the batteries are full, where are you going to put the energy that's being captured? And if you don't load that system, that piston will go really fast and smash into the end, and bad things happen. So there is a heater down there that when the batteries are full, it detects that and it directs the energy, electrical energy, it captures into a little heater. And it's not contributing to global warming because it's taking energy out of the waves and putting it back into the ocean as heat. So it's okay. But anyway, it's a not very complicated system, but it's a very specialized system because, as I said earlier, this is, I guess, 2 minutes of operation of the system, averaging 329 watts of power capture, but it comes in these like 3 to 6 kilowatt gulps every 2 seconds. So you have to deal with this very wide dynamic range. Every wave, that motor is going from plus 3,000 RPM in one direction to minus 3,000 RPM in the other direction. So therefore, the three-phase voltage coming out of that, the EMF of the motor is going from 0 to 300 volts or something each cycle. So you have to be able to convert that to a constant DC bus that can charge the batteries. So this is what a motor driver does, and it doesn't seem like it should be that hard a thing. But when you go out into the marketplace to try to buy something like that, you find out that a lot of motor drives are developed for factory applications, and they're missing a couple of features. Efficiency across that wide range. They have a lot of features. Oftentimes they'll have a web server in them, a million features you don't need. So they're burning a lot of power, just kind of doing their own servicing. And then the biggest problem is when things go wrong in a factory, like it sets a fault light and somebody goes over there and hits the button and resets it. We don't have that option in these autonomous systems. They have to kind of live that way. So that drove us to develop a specific power converter for this application. And this is a prototype. I should get a better picture, but there's a DC link capacitor there and a transistor bridge across here. This is mounted on the end of the motor. And then the cap of this is the load dump. So it's all very integrated into a subsea housing where it's all happening locally here. And there's a computer it's actually pretty rudimentary technology now. It's a 16-bit fixed-point DSP that's closing the control loops to modulate the current in the windings, the quadrature and flux current in the windings, as well as the load dump current and the battery voltage and a number of other sort of monitoring systems. So that is a custom designed item that is a 350 volt bus and can deal with 35 amps of winding current. So it's about a 10 kilowatt system. So it can deal with the 10 kilowatt peaks, but by doing it ourselves, which was actually completely fun to do, although kind of questionable use of resources to design your own motor drive, but it was great. We ended up with a lot of control over the intricacies of how it works. And in fact, every time this system, as I said, it's going from minus 3,000 to plus 3,000 RPM every cycle. Well, down below 300 RPM, we don't have enough EMF out of the motor to boost it up to 350 volts economically or efficiently enough. So it's just kind of lost. But the thing is still, we're switching current in the windings across 350 volts at 20 kilohertz or whatever the switching transistors are doing. Well, it's 20 kilohertz. I know it's 20 kilohertz. So that's a lot of switching loss. So it's like 35 watts of switching loss, which isn't a big deal when you're making 1,000 watts, but it is a big deal for that couple of seconds as you bring through zero and you're not moved. By having control. So there's that, and then the autonomy features. It knows what to do in kind of like every case inside a microcontroller that doesn't have an operating system. And, it's more or less fail-safe. The surface buoy can communicate with this power electronics over CAN bus, much like kind of car network works, but it can't, in theory, it can't tell it to do anything that'll damage it. So the microcontroller has its safety features built in. I'm going to talk a little bit more about that. This has been a pretty good success, this power electronics. There's another related project at the University of Washington Applied Physics Lab where they have this tidal turbine, which is this, I don't know, it looks like a cartoon, but it's this big motor that sits and it's this cross-flow turbine, and they put it on the seafloor in tidal areas, and every 6 hours the tides come and spin this around. And this is a big motor down here, but they had the same problem. They were getting this power electronics designed for factories from Siemens, and it was burning up all their power just to keep their power electronics on. So we've implemented our power electronics in the end cap of this system now in a collaborative effort with them. And it was neat because this thing is a 100 RPM device. Ours is a 6,000 RPM device. So it's a 60 to 1 ratio of speeds, but their voltage constant of their motor was 60 times larger than ours. So the voltages turned out to be the same and the currents turned out to be the same. And we just retuned our control loops a little bit and put it in there, and it's working well. So that's up there. So these are all boards that were designed and built at Ambari, DC link capacitor, six transistor bridge. Those are the 6 drive circuitry power supplies, sort of a power conditioning choke. And then, there's a processor there too. So anyway, so I think that I wanted to, before I get on to what we're using this power for, I wanted just to stop there on the topic of power electronics. And I think it's a super interesting field right now in that electric cars and transistors are to the point where these sort of brushless servo motors are just turning up everywhere. And the chipsets that are available to control these things and do the Park-Clark transformations and field-oriented control and all these things are finding their way into hardware developments in chips. TI makes an interesting series of parts. And I think there's just a sort of, my read on it is there's a lot of applications for this, and it's making its way into consumer goods. Like I have a new washing machine in my house, and it says direct drive on it, and you're like, what does that mean? But you can just tell the way it operates that it's a sort of motor in there. It's not an induction motor. So, and when these, applications where the power is doing regenerative braking, I don't think my washing machine is doing regenerative braking. It might be, but putting it back on the mains lines, I think this is all becoming possible as these transistors become more available. We're building a new ship in Abari, and the motors on that ship are diesel motors, 1,000 horsepower, connected to a 1,000 horsepower electric motor, which then goes through a six transistor drive, very similar to this, onto a 1,000 volt DC bus. And then that power is gone somewhere else to turn the thrusters. So these IGBT FETs are at this point where it's 1,000 horsepower, 6 transistors, 1,000 horsepower. I don't know. I think it's pretty incredible. But moving on. So I just wanted to touch on that. This is electrical engineering department. And I think personally, I've got pretty interested in the power electronic side of it. And I think there are applications for sort of very specialized. It's a whole field of knowledge that I think is probably going to be pretty important. So, in any event, what are we going to use 200 watts continuous for? One thing about oceanography is we've had like 50 years of developing instrumentation at a very low power to deal with solar panels and battery packs. So there isn't actually a huge demand for on-buoy instrumentation that burns more than a couple of watts. There's a few items. One is something that we are deploying on our buoy right now called the imaging flow cytobot, which is a plankton microscope. I'll give some details about that. And then our real application that we've sort of done all this work for is autonomous vehicle recharge. So we have some programs around those 12-inch diameter AUVs that I showed in the first slide, docking systems that are going to be connected to this system to recharge and sort of live at sea. So I'm going to start with I'm going to quickly go through the plankton microscope. This is a product. This is an instrument that is designed at Woods Hole Oceanographic Institute, and it takes pictures of tiny little plankton, which I know almost nothing about, but I'm going to tell you some things. And this thing is about a 45 watt device and makes thousands of images every hour. So there's just gigabytes of data coming off of this thing. So this has been deployed in our buoy. It's mounted here and pretty much the last couple of years. And it's actually in collaboration with the UCSC professor, Rafe Cadella, and a graduate student named Patrick Daniel, who's done this data analysis work. But what comes out of this is pictures like this that are just all these little plankton, and I don't know all the names, Trichoceros, I guess. But Patrick has developed this classifier which converts these images, which come out every 30 minutes. You get back images like this. He has sort of a machine learning algorithm that basically provides a histogram of what's there, and then over months, he can determine what's going on with blooms and this sort of stuff. And they've done pretty well on the machine classifier. I hope I put Patrick's name here, but this is some idea of how well it does. And I'm not going to talk about that. This is not my area. But this is part of a series of instruments funded by the state of California to detect harmful algal blooms in the ocean. I guess maybe they think the surfers aren't going to go in the water. But there's about 7 or 8 of these funded by these imaging flow cytobots up and down the coast. And they're all on piers, Stearns Wharf, Santa Cruz Wharf, Bodega Marine Lab. But there's only one that's offshore, and it's because it's on our buoy. And it's only one is on a buoy because we're the only ones with power to power it. So it's an example of how when you bring the power, you can start to do hopefully interesting things. And there's a whole series of science coming out of this that's tracking the arrival of harmful algal blooms at our site versus the Santa Cruz Wharf. And they're looking at modeling and dynamics of that in the bay and a whole bunch of stuff I don't understand. But maybe for this group, more interesting is the autonomous vehicle docking project. And in the last couple of years, we've been working to dock our long-range AUV to some infrastructure to recharge it. And we've been pretty successful with that. And this system right now is working as a vertical rod here. So there's some control electronics here and a camera and stuff and a float. And the basic dock is very simple. It's an anchor on the seafloor with a float. And then there's this vertical rod section. You can see it says niobium dock. So this rod has 2 contacts of material, the element niobium, which is on the periodic chart, like next to tantalum, it's a transition metal. And it has a super interesting characteristic. Well, before I get to that, I'll say that it is currently connected with a seafloor cable to a surface buoy with solar panels and radio. So we can talk to this electronics sort of in real time while it's out there. But the way this works is, let's try again. the vehicle has this arm in it, and the swims into the rod here, and this rod closes on it. You can see there's two electrodes on there. There's two sort of independent pieces of metal, and that rod closes, but it's still free to move up and down and slide around. And there's three contacts coming in, which then transfer the power. So there's a big question, like, how does that not short out in the seawater? And the answer is this material called niobium has a characteristic in that up to 60 volts, if you put a potential across the two electrodes on the rod, it passivates. A very, very thin layer of some sort of oxide develops on there, and no current flows across that gap up to 60 volts. It breaks down above that, but it's only like a 1 or 2 atom thick film. So when you fly the vehicle in with these little brushes that stick up against it, it scrapes that film away, and current flows across the gap without going into the seawater. So it's sort of a miraculous solution, and it has allowed us to do this dock in a way which doesn't rigidly constrain the vehicle. Before we had sort of come across this, any AUV dock looked like a big garage where we flew the vehicle in and had to rigidly constrain the vehicle and then line up inductive charging paddles, which require very close alignment because of the magnetic field and the electric field, or plug in a plug, which was almost quite the same alignment, so it was almost easier. But it meant this huge subsea structure because you had to kind of capture the vehicle and constrain it. It also meant the vehicles, which are, our vehicles are all swimming vehicles. They rely on moving forward for maneuverability. They can't stop and hover. So you have to bring those vehicles in at like 3 knots, which doesn't, 3 miles an hour, which doesn't sound very fast, but the things weigh 1,500 pounds, so it's a bit of a crash landing. They have to come to rest within one of their own body lengths. So that was always a problem with the big garage thing, was they were beating the heck out of the vehicles. So anyway, niobium was this whole concept of using niobium, the material, was developed by Northrop Grumman, and they call it Neobicon because they need, a trade name on it and stuff. But it uses niobium, and I talked about how it works. And so we have a license. That was a little tricky. They have a lot of patent and intellectual property rights around this. So we have a license agreement with them to implement that system in our AUV docking. So that's been kind of what we've been working on the last couple of years. And this, hoping it starts. Maybe I'll have to do it again to start. But this is a sort of ride along. This is a camera that's sitting on the side of the vehicle, swimming towards the dock, which is this bright light right there. And this is the capture arm here on the right. I'm hoping I play this. Let's see. Yeah. So it's swimming along here, and it's using sonar to navigate to this dock. And eventually you'll see the rod right here. And then it navigates via sonar. There's a sonar transducer down below, and it rattles in here. And there's a little photo cell here that detects that the dock is present, and that closes the arm, sort of captures it there. And once that's closed, those 3 brushes touch the 2 electrodes of niobium, and current starts to flow into the batteries. And of course, the polarity, as it swings around, the polarity changes on those 3 brushes. So there's a diode rectifier, very simple, to turn that back into DC to charge our batteries. So that's how that works. I think there's another cool video. So there's a camera on the anchor looking up the rod here. And it'll become a little more clear as the vehicle's light shows up on the scene. So the vehicle is swimming in, and there, I don't know if that was the same capture or not, but you can see the vehicle came in there, and now it's detecting the rod, so it says, okay. And you can see the vehicle yawing around. So I mentioned the story about like the big crash landing in the vehicle. There's a lot of potential energy, or kinetic energy, in the vehicle moving along at 3 miles an hour. That's got to go somewhere. And in this case, we didn't really expect this, but by putting the capture rod off on the side there, it's yawing around. So a lot of that energy goes into yawing the vehicle around. And there's, it's just like a 15-pound float up above. So the whole thing has some flop forward and aft. So it's been much more gentle in the vehicle and sort of tolerable. It hasn't shaken the vehicle to pieces. Yeah, so that's now the vehicle's on the dock, power's flowing. And then we also impress a higher frequency signal that carries Ethernet, IP traffic over the same connectors. And that's kind of standard power over Ethernet over power line componentry that you'd use in a home network or something.
Is that impact why you separate the dock from the main buoy?
The reason we separate the dock from the main buoy is mooring lines are very efficient at moving wave energy down the column. So everything's moving. And we dream of that, being able to dock this below a buoy and have it just kind of live. I think in a deep water buoy that might work, because as you go down about 1,000 meters below the surface, there's enough side-to-side drag in a mooring cable that it tends to only be moving vertically. So we sort of dream of being able to fly it in and not having a seafloor expression, especially in deeper water. but we haven't done that yet. But that's the real reason they're separated. Yeah.
What happens if you miss the docking point?
Just keeps going. So people ask us, well, what's your percentage for hitting the dock? Well, if it misses, it just tries again. So I'd say 100%. Yeah, it about every third time it'll miss for any number of reasons, control system problems typically. It's using a kind of lousy ultra short baseline sonar to locate the dock. It's not that great a sonar. I think if you could do an optical termination Holman or something, you could do a lot better. If it misses, it just keeps on going and it detects that it's beyond its waypoint. And what it does at that point is it turns off its thrusters and it drifts for 5 minutes or something, and any current will take it downstream. So on its second pass, it's always coming directly upstream. So that's, it's kind of, it doesn't know the current ahead of time, so it just kind of guesses and goes in. If it misses, then it just stops, drifts downstream, 20 minutes, tries again. And typically we hit it on the second try in that case because we're coming directly upwind at that moment. Yeah, it's a cool project.
You have experiments where you can show that this can be perpetually underwater.
We're getting closer. We're getting closer. So this is one of our first shots of it. I love that black and white picture of the camera. And this was in our lab. Like, this is the ultimate screenshot. I took my phone and took a picture of the monitor. But so you can see at this point, we were charging at 24 volts and like 8 amps. So, but right now we're up to, you can go up to 60 volts before the oxide layer breaks down. So we're running at 48 volts, a very convenient voltage, and we're up to 10 or 12 amps. So we're sort of charging at 500 watts or so. And it's a 6 kilowatt hour battery on the vehicle. So, you know, it takes 6 or 12 hours to pull, you know, charge it all the way up, but that'll give you a couple of weeks of use in typical usage. So, and this spring we had it out right here off Santa Cruz. The board, this is exactly where it's still located. And we ran a bunch of science experiments where it's a plankton population study. So in the spring, we get this big upwelling where the wind blows down the coast and eastern boundary current story, and the cold water comes up off the seafloor and brings a lot of nutrients with it, and the phytoplankton go crazy. So we have some scientists that are interested in those processes. So every night they would, every day they would sit on the dock and charge up, and then they would drive up to Davenport overnight and do plankton studies, and then they'd do that one day and then into the shadow here where there's less upwelling inside Monterey Bay. And they would alter that every day. That was our ambition for the spring. It was our first time we tried to do like regular docking, you know, routine use. And we sort of advertised it to our science group of like, yeah, you know, there might be issues. And they were pretty cheerful to work with us. And then we, you know, we did a lot of technical debugging mostly in this deployment, but we're getting closer. And at this point, for a while, it took a lot of care and feeding because it would just be finicky, but that's getting automated now. So at this point, it is kind of running every day, docking, charging, and going off on its own. But the solar buoy is only 15-watt buoy. So, you know, and it's, especially this time of year, the sun's not out very often. So we're really quite limited power on this system. So it's a neat demonstration, but it's not saving us that much. Now, next year, we're going to move this to the wave energy system, which, you know, this is kind of a hard thing to see, but the buoy floats with the heave cone below. Currently, the anchor comes off the bottom of this and goes to the seafloor, but we're going to change the mooring configuration there and bring the power down this long electromechanical cable to the AUV dock over here. At that point, we'll have much more power available, but it's a electrical engineering transmission line problem now because, you know, this is a couple hundred meters of cable, which there's a lot of IR losses. Or I squared R losses in terms of power down that cable. So we're going to transmit the power down at our 300 volts, so the ground fault concerns and safety concerns. And then, of course, a cable is hundreds of meters long with 2 wires that are right next to each other. It's a big capacitor. So when you turn the switch on, like, it's a big capacitor and there's big inrush current. So all these things have to get managed. Sort of typical electrical engineering stuff. DC system. But really, this will be exactly the same as it was before. It's just connected to a different power source.
Quick question: how do you position underwater? Are there any beacons to use relative distance with sonar and guidance?
Well, usually not. Usually, most underwater navigation occurs as dead reckoning. So at the surface, you have GPS comms, and you can get a good GPS position. See you, Gabriel. Thanks for coming. You can get a good position, and then once you're underwater, you're getting more and more lost all the time. And the rate at which you get lost depends on how much money you spend on your instrumentation. So this vehicle has a sort of a low grade AHARS inertial navigation system. and a DVL, so 4 beams of sonar that are picking up the seafloor to measure velocity. So it's getting lost at the order of like, you know, 0.5% of distance traveled or 1% distance travel or something like that. Now you can spend a lot more money on more power and hungry inertial navigation system and do much, much better than that. But it is always that nature of it's integrating acceleration to determine position. So it's always adding up that error. So you need some reset and fixed position. Any given beacon would know that. So the AUV dock does have a sonar beacon, and we know where that is. We anchored it there. So that is getting fed back into the Kalman filter to figure out to help aid the navigation. But that's pretty unusual to have a known beacon on the seafloor. I mean, it's done. Sometimes, if you really want very accurate positioning underwater, especially before we had as good an INS as we have now, you would use a long baseline system where you put 3 or 4 beacons down, and then from the ship, drive your ship in a big circle or figure 8 over them with a bunch of ranges, slant ranges to it, GPS measurements from the sky, and then you'd be able to locate it accurately. And then the vehicle down below would be pinging off 3 or 4 beacons. So you can do all that, but it's a huge job. Like you're going to spend a week getting that network in place. So it tends to be not that convenient. So
the trajectories on your plankton experiment, those are probably not straight lines, and they're kind of relatively in that direction, like toward Davenport and back to the bay, right?
yeah, right.
It's like
Exactly.
roughly.
Yeah. I think it probably comes up along the way at one point and gets a GPS hit. So, but for that experiment, they don't really care exactly where they are. They just need to know they're in the neighborhood because there's big patchiness. So.
How about using some signatures on the seafloor or
Yeah, of course. And there's a couple of efforts that have already going on in that direction. Steve Rock, faculty, now retired faculty at Stanford, has for many years worked on something he calls terrain relative navigation, which relies on having some map of the sonar as a particle filter to determine where you are relative to the known map. And then the ultimate, of course, and we talked about it earlier when we were talking, is SLAM type work where you're doing simultaneous localization and mapping. And one of our principal engineers, Giancarlo Troni, who I think y'all may be familiar with, is working in that direction. So there's a couple options there.
And then to dock to the port, the charging port, is that an easy control problem, or you need to kind of find your way around by kind of circling around?
In principle, it's an easy control problem because the sensor on the vehicle is a range and angle sensor, and so it's ultra short band of baseline, gives you range and angle. The problem is it's a lousy sensor, so you're doing a lot of filtering on that, and I think we can do better. But the problem is once we started hitting it every other time, everybody stopped trying more or less. And then they said, Andy, can we make the arm longer? It'd be easier to hit. And I said, no. And I'm like making it shorter so they try harder. But, so I think it could be much more optimal with a better sensor. You always make your control problem better with a better sensor. Like the best way to do better control is to spend more money on your sensor, which is not that comfortable an answer, but it's also true. And then there's a lot of work to make good navigation with bad sensors, and that's a super interesting area of research, but it doesn't take away from the fact that if you have a better sensor, you have better nav. So. Yeah.
Okay, so so just quickly on the I guess the big problems are drifts, I guess, when you are docking to that.
Yeah.
And just can you make a comment on that? And then the other thing is that you show us the docking, but you don't show us undocking. So how undocking works?
Undocking works. The truth is, I don't entirely know. It opens the arm. I know that.
Okay.
And I think most of the time the currents sort of blow it away, and it detects. It's got a DVL, so it knows its velocity over the bottom, so it's navigating, and it'll notice that it's 10 meters from the anchor, and it turns on the propeller and swims away.
Okay.
Now, what we haven't done very well is like emergency undocking. Like if something goes wrong with the computers, like it's stuck down there. So we have some work to do around some fail-safe, behavior, so that no matter what happens, we don't have to go out there. Swim down and get it. So that hasn't happened yet. I'm worried about it. So. All right, we can cover that. I want to talk. So that's AUV docking. A lot of the motivation for this project. Super interesting project to this probably people in this room. But I want to talk a little bit about wave energy conversion and some of the technical challenges and some opportunities to do some collaborative research, perhaps. Wave energy conversion is like a super hard problem. Reliability and storm survivability is a big problem. Every year we get about 3.5 million wave cycles on that buoy, so that thing is stroking in and out and going from minus 3,000 to plus 3,000 RPM like 3 millions of time a year, including millions of travel of that hydraulic ramp sliding in and out. So There's a ton of reliability engineering to make that work. We have that pretty much solved at this point. But the fundamental issue with wave energy is we're designing the system for maximize the forces. There's power is speed times force. The speed of the wave, like, we can't control. It's not very fast, A, and B, it's what comes in nature. So we can't speed that up. So the only thing we can do to capture more power is to increase the force. So this is like one of the few things that we design and build where we're not trying to minimize the forces. You're building a bridge or a mooring system, you're trying to get the smallest forces in the system as possible. But in wave energy, we're designing for the maximum forces. So that makes it a sort of unique and difficult engineering problem. I've been trying to think of other examples where we're designed for the maximum forces. I don't know, but now there are some control systems approaches to help with that, and I'm going to talk a little bit about that. The system natural period, at the size of what we're doing here, the natural period of that system is like 2 seconds or 3 seconds. The wave energy in ocean is more like 10 seconds. So we're not at a resonant frequency. We're at a wave following frequency where the system tends to just want to go up and down together. The plate goes up and down together. And we're really just taking a fraction of what's available in the waves because we're not at a resonant frequency. To build something at a resonant frequency, it's a big building, so it's a problem. The simplest approach to the control problem is to sort of exert a force resisting motion that's proportional to the velocity of the piston, like your everyday damper. And that's what we've done in our system. So it's like the dumbest possible thing. And it makes power. And we can see that when we get, after you all live here in the spring, like April, it's windy in the afternoon, it gets choppy. So we can see in the morning when it's foggy and calm and like an oily long swell seas, we're not making much power. And then 2 o'clock, the wind comes on, and that short period energy turns up in the wave signature, the power jumps to 800 watts, like in no time. So you can definitely see that effect. Now, the question is, are the control system approach is to kind of adjust and do that? And there's been a lot of work in model predictive control in which you're modulating the force applied to the piston or motor in our case, on a wave by wave basis, such that you're sort of artificially shortening the natural or lengthening the natural period of the system. If you could do that, you can make this whole device smaller. One of the big limitations of the system now is it's pretty big. Even with a big ship, it's kind of a big, heavy thing to deploy. We also, as I mentioned earlier, have a stroke constraint of 2 meters, and the previously mentioned large ratio of peak to mean forces. So there's been a lot of work around in model predictive control and simulation that can demonstrate that if you know the incoming waves, big if you know what the incoming waves are, you can modulate the forces using model predictive control to increase the amount of power you're capturing in any given device. So this is a simulation I did, like in MATLAB. The blue line is the linear dampers control law that we've implemented here. So you can see that the mechanical power absorbed here is this is 45 seconds of operation here. So the mechanical power is sort of bubbling up each time. It never goes below 0 because it's a damper, but it goes up to, 400 watts, 800 watts. This is in a reasonably small C state, but it's always positive and relatively small. If you do model predictive control, where this controller can be looking ahead and see what forces are coming, it can kind of position the two items to be far apart. So when a big swell comes, it pulls extra hard and extra far. That allows you to get considerably more power, like 5x the amount of power capture on average, and it comes in big peaks. Suddenly this is the same C state running in, but suddenly the peak powers are much higher. You'll also notice that at part of the wave cycle, you're putting power from the battery back into the wave field back through the system. So you have to have 4-quadrant power electronics that can flow power each way. So this is an area of wave energy control that's been super well explored in simulation. There's tons of papers showing how to do this. It wasn't hard to do this quadratic programming solution of this problem. This is a linearized thing. There's been a lot of work in nonlinear model predictive control in the same area. And I have not seen anybody that's demonstrated at sea. So it's out there as a problem. Now, one thing that we have going on with our system at work or at Amari is we have a grant funding from the Department of Energy to make our system available to other researchers to come in and do some of this work. I have limited staff and bandwidth to do a lot of these projects. And the Department of Energy has a lot of interest around wave energy and fund a lot of research projects to do technical development and this sort of thing. So they have funded us to make our system open and available. And the idea is that our system's out there all the time. So if somebody comes along and wants to write some control laws for our system, they could, and then we would help them put it out there. So that's the goal, to make our Embari wave energy converter available to outside researchers. The approach we've taken is to implement ROS2 in our system, put in all the appropriate message passing stuff. And I think everybody in this room probably knows what ROS2 is, so I don't need to go through this. But so previously we didn't have that running. Now it's all controllable via ROS messages, which basically means at any given moment from that Linux computer on the surface, you can tell it how much force to put into the piston. Like that's the main control valve. How much am I resisting or helping the piston move in and out? Plus all the telemetry of the system is also published in ROS messages. The speed of the piston, the speed of the motor, everything we measure is available in a message. So the idea is control laws, reasonably small piece of software, which is reading that, all the state information and determining what control it might want to give at that moment. The architecture of this system is, as I said, there's like a little Linux computer on the buoy with an Ethernet network, ROS based. And then throughout the system, we have these microcontrollers, one at the power converter. There's one at the spring controller, which is measuring the piston ram position. There's one on the heave cone, which measures acceleration and motion of the heave cone. There's one in the battery. But it's very much designed like a car CAN bus connected thing where there's all these different controllers on a CAN bus and then a supervisory Linux computer, which is running ROS. At one point, we had a radar because we were interested in measuring incoming waves. That's gone right now. And of course, there's a GPS and an AHRS on the buoy. But the Linux computer is running ROS and has the needed drivers to talk to all this stuff. It has some short communication processes, some various oversight processes, and most importantly, some possibility of implementing this advanced control type thing that I said. Now, all those microcontrollers are smart enough to not need that. Like if there's no messages coming from the Linux computer, if it's turned off or something, they will continue to implement the default linear damper law. So they're also smart enough, I think, to not like allow you to do anything that'll break it. But anyway, the idea of this is that, of course, to do this, like you guys are clever, but I don't think you can just write some software that I can download onto my buoy and have it work on the first try. So of course, some simulation environment is needed. So we built a simulation environment that replaces the physical buoy and CAN controllers with a digital twin of that here. And all this stuff is all the same. So this simulator was developed under funding from the Department of Energy and is now available and matches really pretty much what is happening on the buoy. So the goal here is that you can write some control software that really can't tell if it's running on the simulator or running on the buoy. And in our vision, other researchers that were interested in doing some work would start with the simulator, prove out, understand how it works, prove out that they can do something, and then under our guidance, take it onto our buoy and try it at sea. So, and we have funding for the next few years from Department of Energy to support that sort of thing. I'm running out of time, so I'm going to get done here. But the simulation environment is done in Gazebo, which is an open robotics supported simulation environment. It's actually been pretty good. It provides the physics simulation, the rigid body dynamics, all these pieces. We had to add a bunch of plugins to it to simulate our power electronics, the free surface hydrodynamics, the wave excitation wasn't in that simulator, so I added that. Flexible tether. Super interestingly, it didn't have it. That and every robotic simulation environment I've ever found has no support for added mass terms. Added mass is, of course, the inertia of the surrounding water that needs to accelerate as the body moves, which unlike normal mass is different in every direction. So it's like a 6x6 matrix, diagonal matrix. So we worked with Open Robotics under this grant funding to add that capability to the simulator. So now Gazebo has the ability to properly include added mass tensor in its simulation. So that's been a good advance for that simulator and was really important for us because that heave cone is mostly added mass. It weighs 1,000 pounds and it has 10,000. It weighs 1,000 pounds. It has 10,000 kilograms of added mass. It weighs 1,000 kilograms. It has 10,000 kilograms of added mass. So you can't ignore that. Like it's real, but it doesn't go left and right. It's added mass more in one direction than the other. So that was good. And as it is now, when running the ROS interface, provides the user software exactly the same message passing in simulation, plus a bunch of information that's only available in simulation, like what are the incoming waves, because that's unknown at sea, what waves are coming next. It's problem. So this simulation environment, it has a GUI, which is cool to look at, but actually, usually you don't use that because if you're doing any real work, you're running it in a faster than real-time environment, which changes quickly. You don't have a problem with that. But I think, anyway, this is plot juggler, but a lot of telemetry comes out. You can sort of see what's going on. We've done some evaluations comparing to our at-sea work and have a paper out a couple years back now, highlighting that. So I'll just give some of the summary data. So in order to make a comparison to the at-sea data, we have a nearby wave measurement buoy that's measuring the incoming waves, but this isn't a phase resolve thing. So we can measure a spectrum of waves, put that spectrum with random phasing into our simulator, and then measure the spectrum of outputs, velocities or displacement or whatever, and then make a comparison in the statistical sense. You can't compare second 12 to second 12 because we don't know what exact waves are hitting the buoy at any given moment. So we did that statistical analysis across 30-minute periods on a whole bunch of spaces in the wave height versus period space. And this is sort of the result. We actually did it in this paper against two different simulators. The blue is the gazebo simulator. So the gray line is sort of unity. So you can see that the simulators are overestimating the velocity in this case and the speed of the motor. And whoops. And of course, the main event, the power, the simulator is slightly overestimating by some tens of percent especially the higher power level. So this is the measured average field power, and this is what it came in simulation for statistically the same wave input. So we're pretty happy with that. It's a super complicated and somewhat nonlinear system. So to have it, we're pretty happy to have it. Of course, you'd always want it to be right on the line, but we were pretty happy with that result. So getting back to the question of outside researchers, as I said, the idea here is that people would come in, write some software against the simulator, which is all open source. I'll go through that in a second. We tried to keep it as simple as we could in ROS 2 in the gazebo. And we have some templates and stuff and some guidance for people like your code here kind of thing. Tutorials and examples, it's all GitHub and Docker installs if you want to do it that way. And there's a website in the upper right is that says embari_wec, I think. It's kind of hidden there, but I can circulate that. But that's a GitHub website that sort of that's the source code for the simulator. And then there's this link to documentation. And there's a page of documentation which leads you through some description of the system. And I think the most important part is the tutorials. The tutorials are sort of set up to kind of take you from nothing to something. Install the simulation, run the simulator, view the messages, and then there's a section down on here, examples on how to add control code and this sort of thing. And then there's a forum where we're there to answer questions. And I think there's a number of project possibilities. If a student wanted to get involved and do something like this, honestly, just implementing the simplest linear damper control would be kind of a cool project and run it on the buoy. And I think there'd be a lot of neat experiences to be had doing that. And you don't get many chances to run code on fielded hardware in the academic environment. But there's also other complicated things you could do, as I talked about the holy grail of some model predictive control. Simulation and implementation. Simulation, of course, first, and then implementation at sea. To do model predictive control, you do need to know what waves are coming, it seems. And that's an area of research that hasn't been cracked. We had a radar system on there for a while. We could put it back on, expand radar, and we weren't ever really radar enough experts to determine what that meant. In spite of having some people from Johns Hopkins APL helping us, we still weren't able to interpret that radar data very well. We've had the suggestion recently to mount an acoustic Doppler current profiler horizontally on the PTO, pointing out radially in 3 or 4 directions, which would give you a pretty carefully resolved velocity measurement sub-sea in each direction. And I think there'd be a neat thing to do to get possible wave fields to that, and it might be possible to improve the incoming wave prediction. That's the sort of thing that if somebody did that, we could add that. Let's say somebody came to me and said, hey, we would add that sort of simulation capability under our DOE funding to make that possible in the simulator. If it came down to then fielding something at sea, we would have to mimic that in hardware, but it's not out of the question. Just straight up system tuning. We really don't know what the appropriate damping coefficients are in the system for optimal wave capture in different sea states. You'd think that would be kind of an obvious and easy thing, but it's not. And then, of course, the other holy grail is things outside my pay grade of reinforcement learning techniques to take things like radar returns, ADCP measurements, incoming wave height, telemetry of the system, and have the machine learn how to adjust the control laws. And that could again be done in simulation first, I think. And again, I don't have much reinforcement learning experience, but of course, sounds cool to me. So anyway, I think there are a lot of project possibilities and then others, and I think it could be done as a research project or as an educational project for people who are interested in that. And you can always contact me. That I'm done here, but the people involved in this, there's been a lot of people working on this for many years. These are staff at Embari, are my colleagues down the left there, and these are some pictures of the time. And you can always, if you're interested in any of this, you can reach me at my email, which is easy. It's hamilton@embari.org. So I ran a little long because you guys asked good questions, but I'm happy to discuss anything else you'd like.
We got some time for questions.
So one thing that would be interesting for us is using the control. So what are the control variables? What to exactly measure, for example, and what is the sampling rate you can implement?
What is the second part of the question?
The sampling rate for, like, say, feedback control loops.
I'm sorry, I still didn't hear the second word.
Sampling
Sampling rate. Yes, fine, thank you. So the main control input is the resistance, the current in the windings of the motor, which reflects to how hard it is to move the piston, the force that's put on the piston through the hydraulic motor and all of this. So the main control input is motor current.
Motor current.
And so that's right now is just all the control laws that are implemented right now are watching the RPM of the motor and resisting RPM, basically, like nearly linearly.
Mm-hmm.
So that's the control input. In terms of the telemetry of what is measured on the buoy, the RPM, the piston position, and therefore the piston speed. The buoy there's a small AHRS on the buoy, so pitch and roll rates and heave rates, maybe not horizontal rates very accurately. It's just a little vector nav VN100. It could be a better system, but it's not a very sophisticated system. There's a GPS on the buoy.
Okay.
So you could have a pretty good motion understanding of the buoy because it has GPS, so you can do a lot there. We have a pretty old school AHRS on there right now. There's a pressure sensor on the heave cone and another small AHRS down there, so you get some pitch and roll. I wouldn't really put a whole lot of merit in the vertical position of that unless you did some state estimation with the pressure sensor, then it might get a little bit better. And then there's the gas pressures are there as well and this sort of thing. So that's the list. And then it's a question of adding other sensors that might be appropriate if somebody wanted to tackle this problem. As I said, for the wave prediction problem, there was a effort. We had some National Science Foundation funding to do some radar work, which was ultimately unsuccessful. I don't really know. I don't have enough knowledge to know whether that's actually practical. We have an upcoming project with the University of Washington and Oregon State University that is going to be putting some localized buoys near the system, like 3 or 4, and then trying to recreate the wave field. Yeah. And that's going to be fun because they will then want to validate their thing by flying drone with LiDAR to measure the actual wave field at any given moment and see how well they're doing. So, I mean, who doesn't want to do that? So those are a couple of other, and then as I said, I thought the ADCP concept of the fluid velocity measurements nearby is actually pretty darn good.
It is interesting that this is a stochastic process. So you're actually trying to, so there is a whole field of stochastic control. You can use it to anticipate uncertainty of.
There is, it's a somewhat non-causal process. So, and there's been a lot of auto regression. You might have seen one slide that said AR techniques. There's been a lot of auto regression techniques in the literature. And that's kind of a lousy literature in that there's some awesome results. And you're like, wow, you can do it, And then you try to recreate yourself and you can't. And then you read the fine prints and they did a bunch of filters. You can only make it work from real at-sea data. I can only make it work, the autoregressive techniques, if I filter the heck out of it in the first place. And I think they did a bad thing. The little bit of literature there is, I think they did some filtering under the covers to make it work, which is really bad.
We can talk about it later.
Yeah, I know there's a whole area there. And what I've done on my limited work with model predictive control is I don't think you need to know the wave energy, the wave height. You really need the wave exciting forces on the buoy. So the incoming wave height, I think you only need to know it 3 or 4 seconds in advance. My model predictive control work has indicated that you don't need it 35 seconds in advance. You just need 4 or 5 seconds and you get a gain. which is, like one wave, half a wave period or something, half a wave.
I have two questions that are somewhat related. So having a single buoy, you're kind of limited to the sensors that you have there. Have you looked at having multiple buoys, and does it have the same kind of effect that you have with windmills, or you have like downwind reductions?
There's a whole field of research on that. What would a wave energy capture array look like? I'm not a believer in utility scale with wave energy. I think it's too complicated and too expensive to compete with the other renewable sources. My interests have been in this scale of things that you can afford to put out with a reasonably sized load and the power of photographic instrumentation. Department of Energy has funded a lot of projects looking at utility scale stuff, and nothing's materialized. I think it's a super hard. Maybe you could definitely do it. You could go make power. I don't know that you're ever going to make it competitively with solar power and wind power.
Another question was, so you're looking at UPC to improve efficiency based on like waves coming in, but I could also see you using it just in high seas, you have these high power inputs, where you could do, we have these constraints, don't hit the top of the bottom. Exactly. Have you looked into that at all?
People have.
Okay.
I haven't. Yeah, that's one of the great promises of the great promise of model predictive control is increased power and constraint observation. Right now, it freaks us out. In big seas, we will come very close to hitting the end stop. And if it hits the end stop, the forces go to the moon.
And you're not applying motor.
Oh, we're resisting as hard as we can. But even in, there's always a bigger wave in the ocean, and it usually comes about the day after you deploy your system. So it's a very difficult environment. And so hitting what we do in our case is, I mentioned the pneumatic spring system. We have a pump in there. We're kind of a little bit caveman in this, but we have a pump in there that can move nitrogen from one side of the piston to the other. So when we see storms coming, it'll pump up the piston a little bit more, which makes it a stiffer spring, which means that we don't bottom out our piston each stroke. But the downside is now it's a stiffer spring, so the inertia of the heave cone underneath, we get a lot more slack cable events. We put a camera on the heave cone once, looking at the cable, and we only did that once because it's horrifying. In big seas, the cable goes looping around. We stopped doing that, but yeah.
This is a basic question, but could you explain the bottom right picture?
Sure. It's my favorite picture. This is the heave cone device, and the upper left is the heave cone device that I mentioned, and it's a galvanized steel construction. These are the three doors. We call it the trefoil because Francois is a French person who trefoil is the word for clover in French, so he calls this the trefoil doors. These three doors, so they can open and close. They're on a motor actuator system, and this is in our test tank in Ambari, where we were hanging it from our overhead crane, and we had a hydraulic ram where we could move it up and down at a prescribed rate. So we were measuring the drag and mass of the system with the doors open and closed by oscillating it in our tank. Wasn't a great measurement because it's only about a 10-meter deep tank and only about 10 meters square. So there's wall effects and free surface effects. So it wasn't a great test, but it gave us some measure of what the added mass of the system was. But yeah, it's a great picture. That's Francois. He's also our diver on the project. So that's him. I love that picture. He's just hovering there.
Question about actually powering the dock. So you have the torque converter on the buoy, and then you're channeling the current through out of DC.
Yes.
Over that long cable.
Yes.
Why didn't you guys just keep it AC and then convert it back to the dock?
Yeah, you could have. The battery storage is that because we haven't done the seafloor expression part of the project yet. Okay. All the batteries are on the buoy. So we have to kind of go to DC anyway. Okay. And we've talked about it. I think that the solar power buoy that powers the dock actually is a 240 volt AC linked to the seafloor. There's pros and cons to AC versus DC. Okay. But it's totally possible. Either way, you have to do a lot of work around ground fault detection and safety issues. That's my nightmare is that we kill the diver. Yeah. It's a good question.
Thanks. Well, lots of interest, and I know you have other projects like we were talking about seafloor mapping and
we do have a lot of projects, and just touching the ones I've been involved in. We have a lot of ROV and AUV control problems, seafloor mapping, LiDAR systems to map the seafloor. And you all are welcome. If you ever wanted to put together a little visit, I'd be happy to show you around the place and see some of the projects up close. We can set that up.
Well, I wanted to also thank you with a little token of appreciation. I know you like coffee, so we got this.
Oh, look at that. Oh, this is
Price
fantastic. Yeah, I'm going to have to get some stronger coffee.
for our.
Wow, thank you so much. This is
For
great.
you.
Great. All right. Wonderful.
Thank you. Speaking again.
Sorry to run a little long. Hopefully.
Thank you for coming.
So, we have, I need the mate on Jeff.
Yeah, sure.
So, how are you gonna do?
Yeah, Bill, thank you.
Like, I love people all. I think this is really cool. We work with all of the folks.
Yeah.
Yeah, but I was just wondering, if, there was any way that, I could send these slides to kind of show the team. Because right now there's like,
Yeah, you bet. Actually, I want to mention one thing before you all leave, and we talked about it at lunch. Amari has two sort of programs. One is a summer internship program for pretty much undergraduate level people. It's a 10-week program in the summer, where about 15 or 20 students come from around the country and world and get kind of assigned a mentor with a project at Amari and spend your 10 weeks. It's a paid internship, paid a little bit. Anyway, so that is something that I think the applications, you can look on our website, mbari.org. That is a internship program. I think the application is probably open after the first of the year in February or so. And it's like a July and August summer program. And if you are interested in doing that, the best thing to do is look really carefully at our website and see what projects are going on and it'll have a list of people like mentors. And you can look to see what projects they're working on and then sort of you got to it's a lot of applicants, so if you can be a little aggressive and call instead of, hey, I want to be an intern, what happens is all these mentors will have to sort through 60 applicants or something. So if they kind of recognize your name ahead of time, it's a little easier. So that would be a tip on how to get involved in something like that. And I can always help with something like that. And then for people who are completing their PhD, we have a postdoctoral research program where at any given time, we have 4 or 5 or 6 postdoc